Hello, ladies and gentlemen. Today we are going to put it all together. We're going to evaluate trig functions, those trig ratios for any angle. For your notes today, you need a calculator, something to write with. Obviously, your notes to take some examples down. Remember, we're drawing pictures, so you need to have your audio on. Now, I don't know why I said that, because if you don't have your audio on, you didn't hear me say it. And as well as that unit circle chart, that's that bright green chart that you picked up in class. That's going to have some conversions on it you'll see here in a minute. So let's review a little bit about converting. Remember that this ties into our whole idea of understanding that circles and actually angles represent rotation. So think about this unit circle. This is exactly the picture that you picked up here on that bright green card. And we need to convert the following degrees into their radian measure. So for example, if I was going to convert 30 degrees, I would do 30 over 360 equals number of radians over 2 pi. And then that would give me an answer right there in terms of pi now. That would be my radian calculation. And I would do the same thing with 45, with 60, with 90. All of these commonly used degree measurements I can convert into radians. We might not know them by heart, but the conversion process of cross multiplying isn't really that bad. Okay, so take a minute if you want to try a few to convert. Pause the video right now and do that, and then I'll show you what those answers should be. Okay, so this is what your unit circle chart should look like after you have converted. This is called the unit circle. It is considered to be a unit circle because we can think about it on a coordinate plane. All of these degree measurements are already on your chart, and these are the measurements for the corresponding amounts of radians. Okay, notice the radian answers always have those pi values in there. The degrees are clearly labeled with the degree measurements. Those are already on your chart, okay? So this is the unit circle chart that you should have after all the radians have been completed. So if you didn't fill out all the radian measurements, go ahead and fill those in. So this is called the unit circle. It has a center at 0, 0. So you may want to write that in your chart there. The center is considered to be at 0, 0 on a coordinate plane. And it has a radius of 1. That means from 0, 0 here out to 360 degrees, the radius would be 1 unit away, meaning that my coordinates right here would be 1, 0. The coordinates on a graph that correspond with this spot or this position would be 1, 0. Let's add some more coordinates. What about up to 90 here? If my radius is 1 unit away, that means the coordinates here, if this is 0, 0, this is the y-axis, this is the x-axis, that means my coordinates right up here would be 0, 1. Over x0, up 1 unit on the y, that's my coordinate for that location of 90 degrees. 180 would be negative 1, 0, because again, if this is on the coordinate plane, my radius is 1 unit away. I go 1 unit away from 0, 0, gives me to a spot of negative 1, 0. And then down here at 270 would be 0, negative 1. Notice how all of those coordinates have zeros and ones in them, okay? But the idea being that we can place this circle on a coordinate plane, and that can help us answer some triangle-related questions that you're about to see here in a little bit. So let's talk more about the whole idea of this unit circle a little bit to kind of tie into our sine, cosine, and tangent. You don't need to draw this whole picture, but we will add some ratios there on the side next to where your unit circle is that says sine of theta and so on. You'll see them pop up here in a minute. So the unit circle, we need to think about our circle center being at 0, 0, and our radius is 1. Don't write this part down yet. I'll tell you when you need to write, okay? So let's think about the whole idea of making this reference triangle. So if this were my reference triangle and this is my theta right here, if I was going to describe the sine, the cosine, or the tangent here, I would in fact use those coordinates that we've been talking about. But if I don't have numbers for the coordinates, I can just speak in terms of general x or y. So if this is the point x comma y, that means this measurement right here would be my y measurement, or my up and down, and this measurement out here would be my x measurement, left and right. And I just got done telling you that on a unit circle, the radius is always 1, so this measurement right here would be 1, because this represents the radius from the center to the outer edge of the circle. Now, if I was standing here at theta and I wanted to write a relationship for the sine, the cosine, and the tangent, as we see there on the side of your card, I can do so using x's and y's. For example, I would set up my sine ratio as opposite over hypotenuse. If I'm here, my opposite is y, my hypotenuse is the radius, or 1 in this case. So I would set up my sine fraction as, that's right, y over r, or y over 1 in the case of a unit circle. Now cosine theta would be adjacent over hypotenuse. If I am here, the adjacent side would be x. The hypotenuse of the triangle is r, so I would say my cosine fraction is represented by x over r. Or in the case of our unit circle being a radius of 1, we would say x over 1. Now the tangent is opposite over adjacent, so y over x would be how I would write that. Neither of those are a radius, so I can't change any to 1. So these ratios, guys, you need to be able to fill in on your chart, or you can write this one too if you like the way that one looks. But you need to add those in there next to where that sine, that cosine, and that tangent is written on that green chart. So our whole goal now then today is to use all of our knowledge, everything we've gained with reference angles, trig function setups, the green circle or the green unit circle chart you just found, and our special right triangle stuff. We're going to put it all together right now, okay? So here are some examples you need to get into your notes. And as I've said before, it's all about the picture. So it says find the exact value of the trig function, and we're going to need to show our work, which in our case is going to be a great picture. So it says I need to find the cosine fraction for the angle negative 225 degrees. The first thing you always want to do is draw a great picture of that angle. So here's my x and y axes, and again, remember with angles, we have an initial side located here on the positive x-axis, and then we're going to go ahead and draw this as a negative 225 degree angle. So I would go down like this would be negative 90, this would be negative 180, and I go a little bit more. If I go all the way up to here, that's negative 270. I've gone too far. So I go a little bit more, and this would be where my angle ends. Now that is the angle negative 225 degrees. But now we need to draw the reference triangle that corresponds with that angle. So to draw a reference triangle, again, you drop it down from the terminal side, the ending side, which is where we're at right now, straight down to the x-axis. And now we need to identify our theta, or our degree measurement, right in here. How many degrees past 180 did we go with this triangle? Well, remember we went negative 225 degrees, so we went past negative 180 a little bit more. So we actually went past 45 degrees, past the 180 degree mark, got me to that 225. So I will have a 45, 45, 90 degree triangle here, guys. That's awesome because now I can use my triangle shortcuts to fill in some missing sides. I don't have any coordinates that go with this point right here. I don't know if it's 3 units over, 5 units up, who knows. But I do know it's a 45, 45, 90 degree triangle. And all 45, 45, 90 degree triangles follow the same ratio pattern. That is, the hypotenuse is the square root of 2 times the leg, or the leg times the square root of 2 will equal that hypotenuse. So the hypotenuse is based on whatever the leg is. Well, if that's the case and we don't have any special numbers here, let's make this easy on ourselves. Let's say that this leg on this 45, 45, 90 is 1. Then the other leg would also be 1. And then I can easily use the relationship 1 times the square root of 2 then to make the hypotenuse. So I have generically labeled my 45, 45, 90 degree triangle. It doesn't matter if it's 1 or not 1 here, guys. We could call them 2's, 2's, and then this would be 2 square roots of 2. It's just that we need to make sure that we have the relationship there, that the hypotenuse is the square root of 2 times the leg. Now notice we place these values on our triangle, which is great because we need those to find the cosine. We may need to make a little adjustment here. According to the location of this triangle, or where it's located, this is actually not a positive 1 value, right? On a graph, this would be over negative 1. This would be up vertically 1, so that makes sense. And the hypotenuse is always going to be positive because we can find that using the Pythagorean theorem. squaring numbers, square rooting them, we always get those positive values, okay? So now that I've made the adjustments to my picture, now we can finally answer the question. What is the cosine of negative 225 degrees? You find the cosine of negative 225 using its reference triangle. So we're going to set up the cosine fraction for this theta of 45 degrees. Cosine is adjacent over hypotenuse. Adjacent to me is negative 1. Hypotenuse is square root of 2. So I know my answer is negative 1 over the square root of 2. But I can't leave the square root in the bottom, so I'm going to go ahead and rationalize that denominator. Multiplying, multiply, I get negative square root of 2 over 2. This is the exact value for the cosine of that angle, okay? So it involves drawing a picture, but other than that, that's really all we're doing and using those special right triangles, okay? Let's do another one. Let's do the secant of 300. So again, a little bit faster now. I'm going to draw the angle beautifully. So we're going to do a positive 300 degree angle. So I'm going to draw on my initial side, 300, this would be 270, a little bit more. Okay, there's my terminal side or my ending side of my angle. Now I would go ahead and draw my reference triangle straight up to the x-axis, and I need to figure out this theta right in here, or my reference angle. So how much farther, this represented 300 degrees, how much farther did I need to go to get to 360 here, since that's this distance we're talking about right here? Well, I would have had to go 60 degrees farther, right? So my reference angle is 60 degrees. Now this is a 30, 60, 90 then. 30, 60, 90. It may not be drawn to scale, and of course in mine it wouldn't be, right? But I would go ahead and label these the same way we label the 45, 45, 90, using the relationships. Since both relationships for the 30, 60, 90 revolve around the short leg, the hypotenuse is twice as long as the short leg. The long leg is the short leg times the square root of 3. The easiest thing to do would be to make the short leg 1. Now in my picture, it's not drawn to scale, but the short leg would be across from the 30-degree angle because the shortest legs are always across from the shortest angles. So this would be labeled with 1. Then the long leg was the square root of 3 times the short leg, so I'd label that square root of 3. And the hypotenuse is twice as long as the short leg. Remember, this is the short leg up here because it's across from the 30, so I would label that with a 2. So now that I've labeled my triangle, I go ahead and adjust according to any sort of location issues I might have. Is this over positive 1? Yes. Is this really positive square root of 3? No. This would be negative square root of 3 because I'm going down there. This hypotenuse will always be positive. So now that I have my triangle labeled, I need to set up the secant fraction. Now the secant is the reciprocal of the cosine. So the cosine is adjacent over hypotenuse. So I'm just going to go ahead and flip it over. I want the hypotenuse over adjacent then. So the hypotenuse of this triangle, remember that this is my reference angle. The hypotenuse of this triangle is 2. And the adjacent side to me, if I am here, would be 1. So the secant of 300 degrees is 2 over 1, or just 2. All right, let's do a couple more here, guys. Cotangent, this one is negative 8 pi over 3. So cotangent I know is the flipped over version of tangent, but I know I need to draw a great picture here so I can get my triangle drawn. Now, if I go ahead and try to draw this picture, negative 8 pi over 3, like what in the world is that? I don't even know what that is. So we need to first convert that to degrees. X over 360 equals negative 8 pi over 3 over 2 pi. And we can cross multiply, 2 pi x, 360 times negative 8 thirds, leave the pi alone. Ask my calculator, I get 960. So I'd have negative 960 pi divided by 2 pi divided by 2 pi. I'd have x equals negative 480 total degrees. So I have negative 480 for my value there. So this is the angle that I'm talking about, and that's the angle that I need to draw. So my initial side starts here, and I would go ahead and say, well, I got to go around negative, that's negative 360, getting me all the way back to where I started. I still have to go, let's see, 480, 360, 120 more. So there's 90 more. This is probably that 120 more right there. So this would be negative 480. Another way to find that location is to do that coterminal idea. If you add 360 to that, because we know it's bigger than 360, we get negative 120. So it's the same as drawing a negative 120 degree angle, if you like to use the coterminal idea. So this is negative 120. This will be my reference triangle then, right here. And how many degrees will I have here, right here for my theta, for my reference angle? In here, I am 60 degrees away from the 180 degree mark, right? If I'm at 120, I have 60 degrees more to go to get to 180. So this right here is 60 degrees. That means my short leg in this triangle is up here, and it is a 30, 60, 90. So my short leg in this triangle is located right up here, actually. So I would go ahead and label that with a 1. My long leg will get a square root of 3, and my hypotenuse will get a 2. Again, we're strategically choosing the short leg to be 1 because it makes the rest of the side leg measurements a little bit easier, okay? Now let's make our adjustment according to our location on the graph. This would actually be over negative 1. This would be down square root of 3. Hypotenuse is always positive, so we're fine. Now, cotangent is us saying I need to do the tangent ratio flipped over. So tangent is opposite over adjacent. So cotangent will be adjacent over opposite. Remember, we're always standing at our reference angle, which is near the origin. So we're going to do the adjacent side over the opposite side. The adjacent side would be negative 1. The opposite side would be negative square root of 3. First thing I notice is two negatives will divide to become positive. But then I can't leave a square root in the bottom, so I'm going to go ahead and place one, rationalize the denominator here, multiply by the square root of 3 on both the top and the bottom, and I get the square root of 3 over 3. So the cotangent ratio for negative 8 pi over 3 is the square root of 3 over 3. Now one more, last one, okay? Sine of 3 pi over 2. So once more, guys, we need to go ahead and convert. Now you're probably noticing the scary little face in the corner. Yes, something big happens here. Let's go ahead and convert. Now maybe you notice on that unit circle, we've already converted 3 pi over 2. Because you have that handy dandy green chart there, you already noticed that that is the same as 270 degrees. Thanks, green chart. Okay, that is the same. So what we're talking about is a 270 degree angle. So we're talking about going around and around and around, and our ending side is right here. And this was my initial side. Now the problem is, guys, if I'm ending right here, how do I draw a reference triangle straight up to the x-axis? I can't angle it this way. I have to draw it straight up. If I draw a line straight up, that's not going to make a triangle. So what happens in this situation? Well, we got a bum deal here, right? It is best to use our knowledge of the unit circle when we have a quadrantal angle. That is an angle whose terminal side makes it impossible to draw that reference triangle. So we have a problem, okay? We need to figure out how we go ahead and draw a triangle or use our knowledge of triangles to still find us this ratio. Remember quadrantal, we've seen that word before early on in our studies here. That is when that angle lands on an axis. And that makes it impossible for us to draw a reference triangle. So what do? Well, we can still use our knowledge of what's happening. We know this idea from your unit circle chart. Okay, we have that copied down. We also know that 270, the angle we're talking about, is right here. Okay, that's the angle. This is the 270. We can't draw a reference triangle. So when we can't draw a reference triangle, we rely on our knowledge of its location on the coordinate plane. So remember that 270, what we wrote on that green chart, was located at 0, negative 1. We can rely on the coordinates then. So 0, negative 1 are the coordinates, and it says the sine fraction will be the y value over the radius. So what is the y value of our coordinate? Negative 1. What's the radius of a unit circle? 1. So my answer is just negative 1 over 1, which is just -1. So it wasn't that bad. It just seems strange because we can't draw that reference triangle. Okay? So this sort of sums up us putting it all together. You can see how all of these pieces play together here to find these exact values of trig functions. We're using our knowledge of special right triangles. We're using trigonometry. We're drawing these angles. We're finding the reference triangle. We're converting. All of these skills come into play when we have to identify these exact values, okay? I want to thank you for taking good notes today. Kincaid out.